Thanks for the introduction. Hello, everyone. Today, I'm going to present the technical framework that we are working on at Witness Chain, the startup building the DePIN coordination layer. So I will explore several key research projects, which are the building blocks of a DePIN for unifying DePIN coordination. So you probably heard of this term DePIN recently, which stands for Decentralized Physical Infrastructure Networks. These networks include essential services such as communication, energy, transportation that are integral to our daily lives. They are usually monopolistic and managed by those major suppliers, national carriers. This is because historically, the economic forces and centralization can help companies to secure their market positions. And this is especially true for digital platforms because the increased user engagement can usually attract more users and increase the value of their services. But physical infrastructure is fundamentally different because their supply and demand are naturally decentralized. It's hard to relocate it and also digitize them directly on-chain. As a result, the economic benefits of centralization are not as impactful as these digital networks for physical infrastructure. So given this, the decentralization or principle of decentralization could actually play a very significant role when building the physical infrastructures. If we have such DePIN framework, which is more accessible, then individuals and those small business owners, which are already spread out geographically, can easily manage and host their own components. You can host your own hotspots to provide network service to your neighbors, or solar panels, EV chargers to build a self-sustaining power station. So one concrete example of the DePIN category, this is also where we start from, is open networking, which is a very old dream for internet to be decentralized, but is not realized in practice because everything was taken over by those giant companies. But we can still observe the tailwinds of decentralization from many aspects. In the networking category, there are likely licensed spectrum like CBRS, and the hardware is becoming more lightweight. And most importantly, the rise of the token-driven ecosystem. And given all these components ready, one key challenge we want to solve is how to stitch things together in a low-friction way, and also incentivize different parties to interact with each other. Low friction means open and trustless. And further, we can generalize this challenge to more broader context of DePIN, not just the networking. And we find two challenges here. The first is in the process of building each individual DePIN, how can we set up the incentive and trust model to ensure that the network can grow rapidly and can engage user participation? And the second challenge considers the coordination among different DePIN categories. So currently, there are many DePIN companies emerged. They may transit from Web 2 to Web 3, utilizing blockchain as the basic payment layer, the basic security layer, but they are still siloed or isolated. This is not the nature of blockchain as a trustless and permissionless digital platform. So we want to provide how to provide the basic interoperability and the functional coordination to bridge these siloed sectors together, and ultimately to unify the DePIN economy. This is the main challenge we want to solve. And so in face of these challenges, our main idea is to establish physical trust, or in other words, the consensus on physical infrastructure states. We identify several key building blocks of such physical trust, including two fundamental attributes: the location, where your node is located at, and bandwidth, like how well your nodes connects to internet. And in addition, to securely import this off-chain verification results on-chain, we propose this proof of diligence to secure the computational results. So it can be think of a bridge connecting the physical trust we establish off-chain to the rest of the digital ones. And in the rest of the talk, I will dive into these three core components in more details. So let's start with the location replication. We know geodata is one of the most important attributes in many applications. In Web 2, it has enabled those location-aware services like online advertising. And in Web 3, even the principle of decentralization itself highlights the importance of geodata. And in this new decentralized setting, there is a clear need for such a protocol that can verify the location without utilizing any centralized service or parties. So we formulate a problem which involves an entity, we call it Wado, who wants to prove its location. And we also have a set of challengers who tasked with answering the question, where is Wado, to determine its location. And the output of the protocol would be some measurement of the location. Here specifically, it's the uncertainty that captures the maximum deviation of the claimed location of Wado from its actual location. And you may know the basic way to identify a node's location is to measure its distance or the ranges of distance to some other nodes whose locations are already known. But the problem is here in this new setting, in a decentralized setting, the participants are not entirely trustworthy. So Wados may have incentives to misclaim their location. They can tamper with the measurements, even corrupt with some challengers to just to manipulate the result. And also, we have to address the problem of how to convert the measurement to distance, because distance is not directly measurable. And the speed at which this internet packets travel can also vary significantly under different network conditions over the same physical distance. So we need to handle those noises from the variation of network conditions and the malicious data generated along the process. To tackle these problems, our protocol contains two parts, each addressing one of the issues and together form a location verification system. So the first part, proof of internet geometry, translates the internet delay measurements robustly to the actual distance. And specifically, it starts with some pin measurement phase where some selected pair of nodes or challengers need to pin each other to measure the delay among themselves. And to avoid exhaustive pairwise pin measurements, this robust matrix completion algorithm is implemented to improve the efficiency. And this protocol is by design can guarantee that even if there are some incomplete entities or the corrupted data, the entire matrix can still be accurately recovered as long as there are enough samples. And further, with the completed matrix, these challengers will learn a robust and monotonic curve that captures the that it actually defines, given a delay, what is the maximum possible distance the packet can travel. So it's a conservative estimate for which can help buffer different network conditions. And further, to improve the robustness and accuracy of the curve, we apply a filtering mechanism to exclude some data points that deviate from the actual ratio. Then in the last phase of the protocol, the proof of location part will apply an adversary trigonometry framework to identify the possible region that Wado could possibly be located at. And the final uncertainty output is the uncertainty. And the protocol improves the basic multi-iteration method by excluding and discarding in each direction the smallest uncertainty measured by the challengers. So we can look at one example here where the claimed location and actual location are different. And this prover is trying to, so it corrupts 2 of the 7 challengers here, where the corrupted challengers measurement are marked in yellow circle and the rest of the challengers are in blue. And this multi-alteration region can only cover this claimed location. So it can successfully claim to be in another location different from the actual location. But the output of proof location region will also capture this actual location, and to make sure that uncertainty is at least as large as the deviation the prover tried to make. And in summary, this protocol can guarantee us the final feasible region will cover the actual location of water. And also it will minimize the uncertainty measured for honest nodes, because honest nodes don't want to make itself to be in a too large region as the output. Then moving on to the second part, we also propose this proof of backhaul protocol. This is part of the proof of bandwidth system with the other components taking care of the service link between the hotspot and the user equipment. And in this proof of backhaul protocol, it focuses on the backhaul link, which connects the hotspot to the network core. So again, in the centralized setting, we've seen many measurement tools used to measure these bandwidths. One of the most popular tools you must have used is speed test. And what essentially speed test does is they will manage a pool of powerful servers themselves. And then whenever there's a challenge, they will select a nearby server, which has high bandwidth, low latency, and low packet loss, to generate a traffic of to flood the connection that you want to measure. And it's very obvious that this method is not open because not every server can join to participate because it's high barrier to entry. And also it's trusted, you need to both trust the prover and the challenger to generate the final measurement results. So to make the system a bit more open, we are thinking of to replace, instead of a single powerful server, we're trying to engage a group of challengers. They can generate the traffic together, and then they will equivalently form a very heavy flow enough to saturate the final link. But still, this technique cannot provide us robustness because it cannot tolerate any failure of those challengers or the corruption between challenger and prover. And another idea to offload the trust from a single party is to make the system interact with each other. Because if the measurement results only comes from the prover, then you can only trust it. If we can get the measurements from also some other intermediate parties, then it can help verify whether the prover's claim is correct or not. So we've seen some basic interactive measurement tools such as Pasture, which uses the information, the timing signal of ICMP packets to collect the timing back from some intermediate parties. But it is well known that this tool is not cannot measure very high bandwidth because of the network filter. So we still face the problem of openness because it will have some requirements of the people who are participating in this system. So a very natural solution would be, how can we combine these two ideas? We can use traffic aggregation to ensure openness, and then we can make the protocol interactive to offload the trust from any single party. The security model here is very similar to the provocation. So there is a prover and a set of challengers, and they can corrupt, and there are many possible attacks. Some example includes this challengers can just refuse to participate in the protocol, or the corrupted prover can collaborate with some challengers to transmit their packets through some external very fast link. And the protocol to solve these problems work as follows. We start with a traffic generation phase, where this set of challengers, they will generate a sequence of packets by signing a message using their secret key. And then these packets are transmitted through the link, aggregated before this backhaul link. So the requirement is that the total amount of packets are enough to saturate this backhaul link. Then the prover, once it receives enough packets from those challengers, it will immediately generate a very short receipt, which contains the hash commitments of all these packets, as well as some hash of the individual, the packets from individual challengers. And they will send back the receipt immediately, and also the proof of inclusion will be sent afterwards to minimize the time used to transmit this response. Then later, those challengers, once verifying this response is valid, they will stop the timer for measuring this round-trip time between themselves to the prover and submit it to some third-party verifier or the blockchain smart contracts. And the median will be picked as the final timing measurements and further used to calculate the robust bandwidth measured by the protocol. So again, let's see the how the protocol can provide us the security properties. So the first good thing is that this protocol can ensure that no prover can inflate their bandwidth. This is a good property when, if you want to design incentives, of course, you don't want the prover to arbitrarily inflate their bandwidth to claim, overclaim their rewards. But it's also possible that those challengers just want to mess things up. Then the second property can guarantee that if the prover is honest, then you can at least get the accuracy of the bandwidth you have. And this accuracy is determined by the fraction of malicious challengers we assume in the system. And the last part I'd like to talk about is the proof of diligence. And different from the Byzantine prover challenger model that the previous two protocols are discussed, here the problem is started under a rational adversarial setting. And this protocol would be suitable for all verifiable competitions. But here, to ensure that the work is diligent in the process of submitting the results. But here in this paper and also today, I will focus on one of its use cases, that is the optimistic rollup. So we'll start from just a brief recap of how optimistic rollup are secured now. The basic idea is everything is computed off-chain, and only the hash and some proof are maintained on-chain. And the states on-chain will be assumed to be correct unless some application raises an alarm. And at which point, this defensive validator will issue some fraud proof or some on-chain verification scheme to resolve the disputes. This basic framework has a well-known vulnerability that how can you make sure that these applications are doing their responsibility all the time, because there's no inherent incentive for that. And in other words, who is watching these watcher applications? So to solve this problem, we introduced a group of independent workers called watchtowers. And these watchtowers are incentivized to recompute all the relevant transactions, even in the normal path. So in a dispute path, they will also notify when they detect some incorrect states, they will also notify the defensive validator, just like how applications are supposed to do typically. And then in addition, in a normal path, to ensure that they fulfill their watching responsibility, they need to generate a proof of diligence to claim extra bounties. And this process is also watched by the watchtower network themselves. And they need to verify the states and also verify the proofs generated by themselves. Then this protocol incorporates a bounty mining scheme, which is generally a self-selection scheme. So all the watchtowers here need to re-execute all the rollup transactions to get a Merkle root of their states, as well as the transaction nexus in Chase. And the probability of winning a bounty is proportional to the the stakes they put in the system. The stakes further provides a negative incentive for punishing those lazy watchtowers who just make some random response from some incorrect proof. So due to the time limits, I'll just briefly go through how we designed the incentive structure. So the incentive structure is discussed starting from a very basic game setting, where we only consider non-cooperative game, and the action is those diligent watchtowers will do their job and submit a proof when they're being bounty, but the lazy watchtowers will submit an incorrect proof calculated from random thing. So in this simple game, the conclusion is very straightforward. Once we design the incentives properly, all diligent strategy will be the only Nash equilibrium. But things will not be that simple if we consider the possible cooperation among these watchtowers. And this is enabled by the smart contract, which can enforce some collusion strategy. Because if you think of why the watchtowers don't choose to become lazy, because if there exists some diligent watchtower, then they will lose their bounty because the different results can be resolved on chain. But here, once we have a smart contract, think of a lazy collusion strategy. There is a leader who just start a contract saying, I will pick a random result, and everyone will join you to put some deposit, and then you'll agree to calculate your proof based on the random result I pick. So with the help of such smart contracts, the lazy collusion becomes possible, and it introduced another equilibrium with even higher payoff. And there are also some other interesting strategies, such as instead of the leader choosing a random output, it can promise to calculate every computation themselves and share the results with others in exchange for some rents. But the analysis will be more completed for such discussion, but the conclusion is there's no pure strategy equilibrium. So we don't need to care about it in the final results. Then the last step of this protocol is to resolve the lazy collusion equilibrium we've discussed before. And the intuition behind this scheme, so the scheme is called whistleblower. And intuition is we can further open a gateway for those colluders to report the collusion. And this is called a whistleblower contract. This contract will further provide rewards for identifying and reporting the collusion for colluders. And once the leader knows that there exists such contract, that at least some colluder will betray the collusion, then they will not initiate the collusion in the first place. So at the end, I would like to summarize the topics I've discussed today in this architecture diagram, which illustrates the core components of the DePIN coordination layer we are building. So the three protocols we've introduced today set the ground for this physical trust. And the physical trust is further linked to the economic trust provided by the existing staking or staking protocols. For example, in practice, our protocols are built on top of eigenlayer with those operators running watchtowers or the challenger processors. Looking forward, we hope that more protocols, more proofs can be integrated into the system to further consolidate the physical trust. Because not like digital trust where a simple consensus algorithm will work for all the states, the physical trust needs more process and verification. And these proofs can work for other physical attributes, or it can be the variants or the compositions of the existing ones. And we've seen many innovations when collaborating with other DePIN partners, such as introducing the energy proofs into our system and building a new variant of bandwidth proof which works for higher bandwidths. And once we have this general physical trust layer, we can further enable this and open up an application layer, just like how people play with Ethereum digital states. They can build their DePIN DeFi protocols the DePIN dApps, or even tokenize their physical assets in a more efficient and verifiable way. So I'd like to thank all of my collaborators, and also thanks everyone for listening and talk.